So here's the part where I tell you I am definitely going to post the slides on my site tonight. You're going to check my site tonight, tomorrow, next week, next month. I've been that guy chasing the speaker and it didn't work out very well for me either, which is why you can head off to robrich.org and you can find the slides online right now. Building stateful workloads in Kubernetes. Here's the slides. While you're here at robrich.org, you'll see some of the things, and thank you for the introduction. Here's some of the things that I've done recently. I'm a Microsoft MVP, a friend of Redgate. AZ GiveCamp is really cool. AZ GiveCamp brings volunteer developers together with charities to build free software. We start Friday after work. Sunday afternoon, we deliver that completed software to the charity. Monday morning, we're going back to work. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp. Or if you'd like a gift camp here in Mexico or wherever you're connecting from, hit me up on email or on Twitter, and let's get a gift camp installed in your neighborhood too. Some of the other things that I've done, school source control basics, mine is chapter 8. That was fun. And I replied to a .NET Rocks podcast episode. They read my comment on the air and they sent me a mug. Woohoo! So there's my claim to fame, my coveted .NET Rocks mug. So let's dig into building stateful workloads in Kubernetes. We talked about this guy. Let's start, before we dig into stateful workloads, with stateless workloads. This is probably where most of the Kubernetes 101 talks leave off, is they crescendo with a diagram that looks kind of like this. I have my containers inside of pods. I have a service in front of my pods, load balancing in front of them. I have an ingress controller in front of that matches DNS names with services. So a user will hit my ingress, forward off to my service, and reach my pod. And that's usually where they stop. That's cool, but we got this. Let's level up. Our application probably looks more like this. Now we can see the things that we had before, an ingress, a service, pods, but my application also has other pieces. My ingress needs an HTTPS certificate. It needs the configuration of what domain it's listening for. My pods may reach out to file storage. Now they need the path and the authorization details, that configuration content. They also need to connect to databases with a URL, a user, a password, a connection string. And then how do I store that file storage and the database cluster here inside of a container? Or do those need to live outside of Kubernetes? That's what we're going to take on today. How do I get the rest of my application into Kubernetes? Not just the hello world and the stateless resources. How do I get the rest, my stateful resources, into Kubernetes? How do we add state? Well, first, let's talk about what is state. Well, here's some state. Nope, these are not the states that we're going to talk about today. We're going to talk about these states. State, it's persisting content beyond the current lifetime. Now, if the lifetime that we're looking at is a method call, then the state is, well, variables in our class. If the lifetime that we're looking at is a request or a response, then the state might be in a data store or on the file system. If the state we're looking for is a machine restart, then maybe we move it off of the current machine into a file share or into a database. The state is the things that live longer than the current request and response experience, the current lifetime that we're looking at. So when we look at types of state inside of Kubernetes, we can look at configuration data, secrets, data stores, file stores, and singleton services. Let's double click into singleton because that's a little weird. I may have services that need to holistically look at the entire system and make a choice. A great example of this is the auto-incrementing primary key. If I have a bunch of different services and they're all running and they're all issuing primary keys, those primary keys may conflict. Or if I need to do a month-end report, I need to look at the entire month together in one place. These singleton services need to be able to know that there is exactly one. Which one is the primary? Which one is in charge? Now, if we have that singleton service, we need to be able to still have the redundancy that we need throughout our cluster. We need, well, maybe lots of instances, but we also need to be able to identify which one is the primary in that suite of services. Singleton services, file stores, data stores, secrets, and configuration. These are the types of state that we'll look at, and there's native support in Kubernetes for each of these. Let's start off with looking at kubectl get all. Now, kubectl get all is really interesting in being able to show us all the things in our cluster. Well, kind of. It shows us all the stateless things. It doesn't show us stateful things, and it does so on purpose. kubectl get all is very specifically designed so that if you were to delete it and recreate it, you would get back to that thing. So they very specifically hide secrets, configuration, all of those durable things that, well, could lead to data loss. Now, the problem is we really want to get to all the things. And so that's where kubectl get all can fail us. As you grab these slides from robrich.org, you can click on each of these blue links and get to the details associated with those issues and questions about why is kubectl get all not returning my thing? Well, because it was designed not to do that. So how do we get all for real? Well, we can do kubectl API resources, and kubectl API resources will return a list of all of the different resources in our Kubernetes cluster, including any custom resource definitions that we may have loaded. So let's take kubectl API resources, and let's run that through awk to go get the first column, grep out the first row, pipe that to zargs, and take each of those items in the column and comma delimit them. Now we have a list of all of the items in our cluster: deployments, services, ingress, secrets, config maps, PVs, PVCs, stateful sets. We've got them all. Now let's do kubectl get that. Now we really do have all of the things. So typing this every time I really want to get all the things is, well, kind of intense. Instead, create an alias in your shell of choice and run that to go kubectl get all the things. Now that's a kubectl get all, but just a caution that when we run kubectl get all on the things that we'll see today, they probably won't show up. Instead, we'll have to ask for them specifically by name, or really get all with kubectl API resources. So there's the punchline. Much of what we'll see today is not in kubectl get all. Then why is it called all? First up, let's look at volumes. When we looked at Docker, attaching a volume is pretty easy. We just specify that in the Docker run command. How do these work inside Kubernetes? Well, a volume is file storage that is off of the current container. Now we'll have that out there somewhere. Maybe it's on a network file share. Maybe it's on an Azure blob store. It's beyond the current machine. That's perfect. Now we'll symlink that into our container as if it was just another folder inside of our container. That's ideal. We've just hooked it up into place, and our application just deals with that folder as if it was right here. Now, the interesting thing is this folder out on the network share or out on our cloud storage will work great at showing all the files, but it is a detached network share, so file locks don't work. A container may choose to lock a file and tell all the other things within that container that the file is locked, but if a second container is reading that same file, it could get the wrong answer. And so it's easy for us to accidentally overwrite files by having two different containers write to the same volume. Creating a naming convention matching our container may be a really elegant way to solve that. So let's look at a pod definition. Now, this pod definition may be inside of a deployment. It may be inside of another mechanism, but let's zoom in on that pod definition. Now, here in that pod, we have the metadata, we have the API version and kind. API version and kind would probably get left off if it was part of deployment or replica set. Then here inside the spec containers, here's our list of containers. Now, we'll probably specify a lot of things, maybe build details, maybe our environment variables. But here, let's look at volume mounts. Volume mounts is that spot where we specify those volumes. Now I'm going to name this one the volume, really descriptive there. And here's the path inside the container to that directory that I've mounted. Now, where is it on the outside the container? Here in the volume section, I have that same name, and I explained the driver and the path. Now, in this case, I'm using host path. Now, that will create a folder on the host machine. Now, if I'm going for durability beyond machine restart, that probably isn't a good choice. But for development and testing, this can be perfect. So I've set it here. This host path, here's the path on my machine, and here's the path that that container will use. Now that's perfect. I'm able to map this durable storage. My application can just write files into this folder as if it always had. And I know that those files can be backed up and archived in the way that makes them much more durable than a pod restart. But now we've reached a dilemma. Who owns the file? Have you ever had that fight over the web config file? Well, ops wants to really control all of the things so that they can inject the secrets that nobody should know. But developers need to maintain that all of the things are in place and all of the rest of the settings in web config are specific to development. And then operations really wants all the IIS settings. Yes, that could be the case here as well. Operations wants to own this bottom part. Developers want to own this top part. So who owns this file? Well, the cool part is that Kubernetes has made a really elegant abstraction here where we can separate these based on the roles, the duties that we have. Now, if you don't have this need for separation in your organization, you don't need to go here. But let's explore this if you do. I'm going to take a storage, a hard drive, and I'll carve it up into little pieces. Each piece I'm going to call a persistent volume. I take the storage and I make them into little volumes. Now I'm going to claim one of those volumes and symlink it into my container. I have storage, I have a persistent volume, I have a persistent volume claim, and I have a container inside of a pod. Now the interesting thing is that developers can specify the persistent volume claim and the pod, and operations can specify the storage and the persistent volume. Let's make sure that all of the storage is backed up nicely, that it's organized well, and I'll just make these persistent volumes available. As developers, I just need to claim one that has the right characteristics, and I can use it inside my pod. Developers handle this side, operations handles this side, and we have this really elegant separation of duties. Let's take a look at these YAML files. First up, a persistent volume. Now here in the persistent volume, we're specifying not only the location on the host machine right here, but we're also specifying other details. How big is this volume? In this case, it's 10 gigs. What is the access mode? Read, write once, read, write many pods can connect to it at once, or read only. I also have a storage class name where I can define, is this a particular type of storage? Now, once I've created this persistent volume with a storage class name, a capacity, and an access mode, now I can create a persistent volume claim that can claim one. Now we need to find a match on the storage class name and the access mode, and at least that much storage. So in my persistent volume, I said I would like to create a 10 gig volume. Here, I'm claiming 3 gigs. So this will match. It's manual, read, write once, and it's 3 gigs. And I've named this to be PV claim. Now there's no hard match between persistent volumes and persistent volume claims other than the match on the storage class name, read, write access mode, and at least this much storage. Now let's take this PV claim and let's set it in place in our pod. We have the same volume mounts definition as we did before, but now in the volume section, instead of specifying host path, I am specifying the name of my persistent volume claim, in this case, PV claim. The pod definition can be owned by developers. The persistent volume claim can be owned by developers. And operations can control the persistent volume, ensuring this data is backed up and organized well. That's really cool. Storage broken up into persistent volumes. Claim one of those volumes and symlink it into a pod. This is a great mechanism so that we can create this abstraction where we have this elegant separation between dev and ops. Now, if we don't need that separation, we can definitely just specify the host path there in our pod definition, and everything works out fine. File storage. So we got our files off of our drive into a durable location. But now, how about configuration? Where is the path to that file share? Or what is the details that I need to get to my database? Let's look at config map. Config map is a mechanism for identifying configuration details. Now, they're read-only configuration details, and we can mount them either as environment variables or as files. Let's take a look at each. Here's a pod definition. And here in this pod definition, we're specifying some environment variables. In this case, I have an environment variable named the message, and my value is hello world. Now, my application can just look into the environment variables that it has available to it and pick out these details. Now, maybe I'm looking at process.env, or maybe I'm looking at configuration, and I can just pull in those environment variables into my application. Now, again, we have a really elegant, simple way of defining them, but who owns this file? Should development own it? Should operations? And we're left with that quandary again. Kubernetes has solved this in a really, really elegant way, where if we need this level of abstraction, we can find it. Here's a config map. Now, here in this config map, I can specify multiple settings. So here's the name of my config map and the keys and values in my config map. Now, in this case, I've identified that my database is memsql, that my logging is enabled, and my API URL is example.com. Now, when I want to map this configuration into place, I can use this name, the config map, and I can go grab all of the environment variables from that config map. Now, I could choose to enumerate them as well, but in this case, it was nice to be able to just pull in all of those environment variables in one spot. So I have in from, and I've identified my config map, and now I can have those details. Perhaps now operations maintains the config map, making them different per environment. And developers maintain the pod definition, just referencing that config map. At that point, maybe the pod definition is identical between all environments, and the config map is different between each environment. That's really elegant. Now I can also map configuration as files. If I don't want my environment variables just kind of hanging around, my application can just read this content in this directory. Each environment variable, each configuration key will have a separate file inside this directory. My application can just enumerate all the files in that directory, open up each one, and get at the data that is part of that key. Now, much like I did with regular volumes, I'm specifying the volume. And now in the volumes section, I'm identifying how I'm mapping that volume into place. So I'm just noting that the config map is my source for this data, and that will create read-only files in this directory where I can get at them. Config map. Config map is great for configuration details that maybe aren't sensitive. But if I want to upgrade a little bit and look at more sensitive secrets, I can look at secrets. Secrets have been encrypted at rest if I choose to enable them since Kubernetes 1.13. We're on 1.20 right now, so it's been a little bit, but arguably that's not very long. And I do need to opt in to enable them. the secrets need to be propagated to every node within my environment because, well, if the pod gets scheduled there, they need to be able to get out the secrets. That means that if I lose one of the machines in my cluster, I should probably consider those secrets as lost and rotate all the keys for all the secrets. But if I choose to enable encrypting them at rest, then that works out well. So here's the YAML for creating a secret. Now, here in this case, I chose type opaque and string data, where I can just specify the details here. I could also choose to, instead of defining it as string data, define it as data, and then I can use base 64 encoded values. Now that's interesting. I've specified my key and value for each of the things inside this secret, but it's really easy to accidentally check in this configuration file. And well, then my secrets are exposed. So instead, we probably want to use the command line. Here's the command line that will build up that secret. So I've created a secret, I've given it a name, and then I have keys and values specifying the various details for each secret. Now, all of these are assigned to that one secret name. So much like here, I have multiple keys and values in one secret. I prefer doing it from the command line to make sure that I don't accidentally commit that YAML file into my source control and lose control of my secrets. So secrets, we can map them in as files, much like we did with config maps. And so here I have the same mechanism in my volume mounts. In this case, I highlighted that it was read-only. That isn't necessary. But now I'm specifying that secret is the source of this volume. Now in this folder will be a file for each of the keys and values in my secret. And now my application can open up each file and read the contents of that file to get that secret. I can also choose to specify them as environment variables. I could say env from, but in this case, I've chosen to enumerate each of them. So here's the value from, it's the secret key ref, and here's the name and key of that secret. So DB connection, and I'd like to go grab the username, and I will expose it as a environment variable to my application named DB_username. Similarly with my password, I'm going to go grab the DB connection secret, and I'll grab the key out of that called password and expose it as a password, DB_password environment variable for my application. So now we've gotten secrets into our application. This is really helpful. We've got persistent volumes and persistent volume claims that allow us to get durable storage. We've got config maps that allow us to configure our application in interesting ways. And we've got secrets that allow us to keep data safe from prying eyes when we need to configure special things. Now, how do we configure, say, a database server? Now, if we have a database that is a single server, then that's easy. We just prop up one pod, point it at a volume. But what if we have a distributed cluster server, maybe an ELK server or a single store database, where lots of different nodes work together to establish quorum? Now, that's great inside Kubernetes because now I have a distributed piece where any one machine is not all that fragile. As the pods are restarting, my database is still online. But now I need a way for those machines to communicate together, to be able to replicate data between them. And that is where Stateful Set comes in. A Stateful Set is like a deployment, but with much more durable and predictable names. So that if my pod goes down and comes back up, it will have the same name as it had before, and I can continue replicating data to it. We can think of a stateful set like a deployment, but with durable names. It's easy for me to communicate between those machines, to replicate the data between them, to discover which machines are online. A stateful set, I might have a Kafka cluster, an ELK stack, a database cluster, something where I need multiple, misusing the term, machines, multiple containers that work together to produce a cluster for this service. Now we're kind of conflating the terms because we have our Kafka cluster, and we have our Kubernetes cluster. Or we have our Elk cluster, and we have our Kubernetes cluster. In this case, the database cluster is all of those pods that need to work together. Now, they're all pods on our Kubernetes cluster, but they need to be able to work together so they can replicate data between them. So here's a stateful set. We have pods and containers inside pods, but we need to be able to discover and replicate data between them. So rather than having pod dash some big random name, this will be pod dash 0 and pod dash 1 and pod dash 2. We now get to be able to identify the specific machine, well, container. And we have this headless service that allows us to communicate between them. Now, we could misuse this headless service to accept traffic from the outside world and route it in a round robin fashion to a particular machine, or specify those machines. But ideally, we're only using this headless service to facilitate communication between the containers within this application cluster. So let's double click into that stateful set and understand the YAML to do that. You can grab these slides from robrich.org, and this is text. So copy and paste that into your application and start to experiment with this. Here's a stateful set. Now here in the stateful set, we have a template, much like we would with any deployment. And here's our pod definition. Now we may include things like persistent volumes, environment variables, persistent volume claims and environment variables. Maybe we're referencing config maps or secrets. Scrolling up a bit, we have our number of replicas. That's the same in a deployment. And we have this one thing called service name. That is the name of the headless service that we use to be able to communicate between our applications. Now, in this case, my service name is called DB service. So let's dig into that headless service. Here's that DB service. And this is a service in all the ways that it is a service, with this one exception, cluster IP of none. That's what makes it headless. It doesn't have a cluster IP. But I can still reference it between these things. So if I'm coming at this service from another machine and I just want to get to anything, I can grab DB service. And that will do the normal thing, round robining across all the machines. And we're able to get at whichever machine is most available. But I can also use this as a DNS endpoint. So I can look at the db1.db service or the db2.db service. That allows me to route between the machines. I can now look at each of the machines in this applications cluster and be able to push my data or pull my data to that particular machine. So there's that stateful set. My stateful set allows me to build up a database cluster where I might have reference to config maps or secrets or persistent volumes to make that data much more durable. Now, together in this database cluster, I might reference persistent volumes, persistent volume claims that make my data more durable. I might have configuration data that references the way I'm configuring this database cluster. Similarly, I might have some file storage up on a network share somewhere. Maybe it's in Azure Blob Storage. Here in my application, I have containers that need access to that configuration. Now, if they need access to that configuration, here's where we use config maps. Maybe we'll use secrets to be able to specify the username and password. Here's my service. My service round robins across all those containers. I might have a headless service round robining across all of the containers inside my stateful set. And then here on ingress, I do have some configuration data to get at the domain, and I probably have a secret associated with that HTTPS certificate. Secrets, config maps, secrets, persistent volumes, persistent volume claims, and stateful sets. We've gotten to level up our application from just a stateless application to including the rest of our application here in our database, in our Kubernetes cluster. Whether our state is across a machine or configuration details or any of the rest of the details that are stateful in our application. We can move those into Kubernetes as well. This has been a lot of fun getting to show you stateful workloads in Kubernetes. For those of you watching the video later, you can hit me up on Twitter at Rob_Rich. For those of you who are here live, what are your questions?